Good afternoon, Algebra 1 students. So Mr. Chen again. So welcome back to my YouTube channel. Welcome back to Chen Math Academy. So this one, it's about the properties of exponent, and also we'll talk about the rational exponent and also the exponential functions. So all those type of stuff. So let's get started off with the properties of exponent. So this one is relatively straightforward. It's something that you guys probably learned from pre-algebra already. So let's talk about like the first couple problem right here. Okay, so let me just snip this page. Okay, here we go. So simplifying the expressions, right? You answer using only positive exponents. Okay, so let me put it right here. Okay, let me just shrink the size here a little bit. Okay, so the first one, it's about simplifying the exponent. So one thing that we noticed, the properties of exponent, as you watch the other part of the video lesson that I have. So see anything like a to the power of n times a to the power of n, it's always considered a to the power of n plus n. So it's a power to sum, product to sum. And then the other one is like a quotient, so a to the power of n divided by a to the power of n, so it's like a to the power of n minus n. So quotient to difference. And then the third one, what we got here, it's a power of power, so a to the power of m to the power of n. So it's a to the power of n times n. And then the fourth property, a to the power of 0, it's always 1. And then the fifth one, so we do have a to the power of negative n, it's 1 over a to the power of n. And then the sixth one, we do have a times b to the power of m. So the product with the power, so this one can distribute the power a to the power of n times b to the power of n. And then the seventh one, which is the a over b, quantity to the power of m. So it's a to the power of m over b to the power of m. And where b cannot be 0. So the first one, using that property, the first one, product to sum, so same base, y. So we combine that 3 and negative 5 together, so 3 plus negative 5, then that would be y to the power of negative 2. And then using the negative exponent property, so negative exponent property, that means we want to convert this one to the reciprocal form, so it's 1 over y squared, like that. And then x to the power of 4 over x to the power of 7, so same base, we subtract the exponent. So we got x to the power of negative 3. Again, negative exponent, we want to convert that to the reciprocal form, so it's 1 over x to the power of 3. And then the other one here, we got number 3, so x to the power of 0, y squared, quantity to the power of 3. So started off with x to the power of 0, so that's 1. So 1 times y squared, quantity to the power of 3, so just 1 times y squared, which is y squared, quantity to the power of 3, so that would be y to the power of 6. And then the last one looks a little bit sophisticated. So again, pretty much the same kind of process using that property number 6 and number 7. The power of distribution and the quotient of power distribution. So before we do anything here, so we want to convert this one to the reciprocal form because that's to the negative exponent. So we need to swap things around. So whatever that we have in the numerator, denominator, we just want to swap those elements. So we got 5y to the power of 4 over 2x squared, quantity to the power of 2. And then for the power distribution, product quotient, so we want to distribute the power, 5 squared, 25. And then y to the power of 4 squared, so then that would be y to the power to power, multiply to the power of 8. And then denominator, 2 squared, so we got 4. X squared, quantity squared, so we got x to the power of 4. Simplest form. And for those who might be wondering, well, what about the property exponent would be a more complicated problem? Yes, we definitely do have something like that. But so far, just stick with this type of properties of exponent. If you guys want to watch more complicated one, watch the other part of the video that I have for Algebra 2. Alright? So now, let's see what else that we have for the next section right here. Okay, so going back to this page. So the next section is about radicals and rational exponent. So definitely we'll talk about those type of properties. So number 5 through 8. Okay, so that's the next type of problem I'm about to show you. So evaluate the expressions Okay, so let's start with some of the basic properties of radicals, exponent, okay, all those things. Okay, so let's just start it off with, okay, so again, I need to minimize the size of this one right here. Okay, so let's see what we found with the properties of radical and rational exponent. Okay, so let's start it off with the basic property. So anytime they see like nth root of a, so this one is written as a to the power of 1 over n. So the left hand side, it's a radical form. The right hand side, it's called the exponential form, or the rational exponent form. And the other one, what we found here, it's like nth root of a to the power of m. So this one can be written as a to the power of m over n, like that. Okay? So what happens if we see anything like nth root of a times nth root of b? So basically this one, it just need to multiply those radical together. So it's nth root of a times b. Okay, so let's find out about the first one. So cube root of 8, so this one, if you break it apart, so it's like 2 times 2 times 2. So cube root of 2 times 2 times 2, then that's just 2. It's a perfect cube root number. And then fifth root of negative 243, similar. So that would be negative 3 times negative 3 times negative 3 times negative 3 times negative 3. So then that would be negative 3. And then 625 to the power of 3 4. So this one, let's just rewrite it as the radical form. So this one, we can always convert this one vice versa. We can go from right to left, left to right. So 625 to the power of 3 4 can be written as 4 root of 625 quantity to the power of 3. So one thing that we know is 4 root of 625, which is 5. Because 5 times 5, 25 times 25 again, so that would be 625. So 625 consists with 4 5. So 4 5, 1, 2, 3, 4. So once you take that 4 root of 625, it's 5. So it's 5 to the power of 3. So 5 to the power of 3, which is 5 times 5 times 5. So then that'll be 125. And then the next one, so negative 25 square root. Well, so far in Algebra 1, this one, it's not a real number. But in Algebra 2, this one would be considered 5i. The reason why that is, so square root of 25, negative 25 can be written as root 25 and then root negative 1. And one thing that we notice, square root of negative 1, it's I, which is an imaginary number. So you guys want to find out about the imaginary number, so watch the other part of the video, imaginary number for Algebra 2. So root 25, then that'd be 5. So it's 5i. If the thing is not saying the real number, then that'd be no solution, or no real simplification. Or just say that, no real solution. Okay, so now let's see what else that we have with the other section here. So exponential functions. So normally students don't do any kind of exponential model, the graph, the exponential growth decay model, until they get into Algebra 2. But let's have some kind of an early introduction with exponential function. As you can see that the graph here, it's considered exponentially growth. So this one is grow dramatically, okay? So after it passed through like certain position. Okay, so let's talk about the graph of the exponential function with the domain and the range. Okay, so I'll just pull this one out here, 9, 10, 11. So we'll just do 1 or 2 problem here. Okay, so for number 9 through 11. So for those you might be wondering the best way to determine the domain, the range. Well, obviously you want to sketch the graph first. So anytime that you want to sketch the graph, you always want to utilize the XY table. So in Algebra 2, we do have another technique for making the graph. It's by using transformation. But so far, we're just using the basic technique, XY table. So for the X column, we do know that X is called the independent variable. If that's considered an independent variable, so that means we can plug in any number, any real number. For example, easy number such as 1, 0, negative 1. So what happens once we plug in 1 right here? So we got negative 4 times 1 4 to the power of 1. So 1 4 to the first power, that's 1 4. 1 4 times negative 4, then that'd be negative 1. So it's 1 comma negative 1. So making a model, sketch the graph. So 1 comma negative 1, so that would be in the fourth quadrant. And then 0, plug in 0, so we got 1 4 to the power of 0, then that's 1 times negative 4. So which is negative 4. So 0 comma negative 4, 1, negative 1, negative 2, negative 3, negative 4. So it's down here. And then what about if I plug in negative 1? So negative 4 times 1 4 to the power of negative 1. Properties of exponent, 1 4 to the power of negative 1, that's 4. 4 times negative 4, that would be negative 16. So then that would be too much. And then what we need to do with those two dots, we just want to connect them. So it's a non-linear curve. And if this one is getting closer and closer to the x-axis, looks like this one is going to be getting very close. Now it's not going to touch any point here. So the x-axis, this one is called the asymptote. It's called the horizontal asymptote. And how do I know that's a horizontal asymptote? Because this one right next to this whole group right here, there's no any non-zero term. So the non-zero term, there's no such thing here. It's just 0. So anytime they see that the extra term right here, this one is called the horizontal phase shift in Algebra 2. But in this case, it's called the value of k. If the value of k is 0, so that means it's always the x-axis, which is the horizontal asymptote. And then for the other part of the function here, we just want to do the same thing. Plug in the number. So we got 1, 0, negative 1. So plug in 1, we got 3 to the power, 1 plus 2. So 3 to the power of 3, then that'll be 27. And then 3 to the power, 0 plus 2, so 3 squared. Then that'll be 9. And then 3 to the power, negative 1 plus 2. So then that'll be 3 to the first power, which is what? 3. And then sketch the graph roughly. So this one, 1 comma 27. So let's assume that 27 is all the way up here. So it's over here. Here's 1. And then 0 comma 9. So we got 3, 6, 9. Okay, so somewhere 9 somewhere down here. Again, it's just approximation. And then negative 1 comma 3. It's somewhere down here. Again, there's no extra term here for that separated constant, so it's always 0. It's always the horizontal asymptote, so this one is getting close to the x-axis. If that x is getting smaller and smaller, so eventually the graph is going to be like this. So this one is called exponential growth. So going back to the domain, the range. So the domain for this graph here, so domain says we can plug in any number. So I would say the domain, it's x, it's all real number. Or you can just say that negative infinity to infinity. And then the range for this one, we do know that the range can be never exceeding the x-axis or anything above the x-axis. So this one is just saying that it's negative infinity all the way up to 0. And then what about the domain and the range for number 10? Similar situation. So domain must be all real number, because that we just plug in positive, negative, 0, all those 3 different types of number. And then the range here, so this one obviously showing that it's from 0 to infinity. Okay, so number 11, that's something you guys can try. So this one shows the value of k, so that means k is negative 3. So negative 3 would be the horizontal asymptote. Okay, so now let's see what else that we have for this chapter right here. It's a lot more things to come. So the next one is called exponential growth and decay. So a lot of students still having tough time with that, the model of the exponential growth and decay. Okay, so let's talk about this one. So we got 15 all the way to 19. But for this one here, we just want to do 15 through 18. Okay, so let me just pull this out. So again, the video that you're watching right now, so this one basically just giving you the idea or the quick look of what the whole chapter is all about, or it might be getting you some kind of summary of the entire unit. So once you're done with the one that your teacher finished lecturing, you can always utilize to study. Okay, so now let's take a look at that. So identifying which one is exponential growth or which one is considered exponential decay. So again, just want to make it smaller. Everybody can see that the screen here. So the first one, number 15. So f of t equals 4 times 1.25 to the power of t plus 3. So it doesn't matter regardless what happened with that the exponent. If this one is all positive, it's all about the matter of the base. If the base is greater than 1, and the power here is showing that it's all positive, so the power here is all positive, greater than 0. So one thing that we notice, so this one, it must be the exponential growth model. You can always plug in some number for x, and then try to evaluate the value for y, and x is getting bigger and bigger, y it's also getting bigger and bigger. So this one is called exponential growth. Okay, so now what about the other one? Would that be the same kind of situation? So y equals 1.06 quantity to the power of 18. It is. So the base, again, if the base is greater than 1, so we got 1.0 for the base. So since we do know that it's 1.06, so which is greater than 1, and the power, it's a positive exponent, so therefore this one is also considered another exponential growth model. And then for those you might be wondering, 17. So 17, let's see, this one right here. So showing that it's 0.84 with positive t, minus 4. So this one, it's a positive base, but the thing is that the base is less than 1. So most likely, this one is going to be considered exponentially decay. So 17, so y, so it's going to be less than, well, it's going to be exponential decay, because the base right here, the base is less than 1. So the base here is 0.84, which is less than 1. Okay, so now the word problem. So you deposit $750 in the saving account that earns 5% annual interest, compounded quarterly. So write a function that represents the balance of t years. And what is the balance of the amount after 4 years? So this one is basically just like a compound interest problem. So we do have two formulas for the compound interest. So one is considered a of t. So that equals p times 1 plus r over n, quantity to the power of nt. So r, which is the interest rate. So the interest rate. And then 1, that means always guaranteed that's 100%. And it's the compound period. So right now the compound period, which is, so it looks like this one is compound quarterly. So the compound period. So if that's compound quarterly, so that means 4 quarters in a year. So n is 4. So write the function that represents the balance after t years. So the equation that we have. So we don't know what that is, the amount, but let's find out the value of the time first. No, the value of, let's see. So it looks like none of the stuff is missing now. Everything's given. But let's set up the model. So we got a to the power of t. So that equals the initial principal, 750. So times the quantity, 1 plus interest rate, which is 0.05, divided by n over 4, and then to the power of 4 times t. Because that's compounded quarterly, so n is 4. 4 quarters in a year. So after we wrote the function here, so what is the balance of the amount after 4 years? So basically after 4 years, we just need to plug in a number. So 750 times the quantity 1 plus 0.05 over 4 to the power of, after 4 years, so 4 times 4. Okay, and now the rest of this, you just want to put into the calculator and just find out what that is exactly. So what's the balance of the amount after 4 years? So the balance of the amount after 4 years. So again, basically using the same model. So for a of t, so that equals the initial principal, 750, times 1 plus interest rate, interest rate, which is 0.05 over 4 quantity to the power of 4 times 4. Okay, so this one, after we convert that to the exponential model, and then we just want to solve for t. So to solve for t, combine this group together, multiply it out, divide it, combine them, multiply by 750. Let's see. This one, you just want to find out the balance, not the time. So for the balance, it's just what? A of t, eventually. So just plug in all those numbers, and then calculate that, find out exactly what that is. Okay, so now the next page. So 6.5, 6.6, 6.7, so now they're becoming relatively easy. And let's see, any 6.8 stuff. I doubt it. Okay, so let's go back. 6.6. So write the next three terms of the geometric sequence. So it depends on what kind of people that students, want to hang out with. So always, there's sometimes, they're like a special pattern in terms of the number. Either the ages or things that they prefer to do, all that. If you try to arrange that from the order, you'll see like a pattern there. So here's the example for the pattern. So decide whether the sequence is arithmetic, geometric, or neither. Explain your reasoning. If the sequence is geometric, write the next three terms and the graph of the sequence. So let's talk about arithmetic geometric sequences. So arithmetic sequence, so that means we can find out the next number by either doing addition or subtraction. So let's say we do have 2, 4, 6, 8, 10. In order to go from one number to the next number, you add 2. From one number to the next number, you add 2. So this one is called the arithmetic sequence. If that's a geometric sequence, so what we need to do is that it's multiplication. So let's say that we do have 1/2, then 1, and then times 2, then that'll be 2, and then times 2 again, 4. Okay, like that. So this one would be the geometric sequence. Keep going on forever. Okay, so now going back to this template. So decide whether the sequence is arithmetic, geometric, or neither. Explain your reasoning. So 3 to 12. So in order to get this number, we either add 9 or multiply by 4. Okay, so we cannot decide yet. So in order to go from 12 to 48, and it looks like we need to multiply this number by 4. So multiply by 4, you get to the next number. What about the previous number? Can I multiply by 4 to get 12? Yes, you may. So that means 26. It's considered a arithmetic sequence. So 27 is quite similar. To go from 9 to negative 18, we multiply by negative 2. But negative 18 times negative 2, it cannot be 27. But what happens if we just add the number? So subtract negative 18 minus 9, so then that would be minus 27. And also that doesn't make sense. So this one I would say that it's neither. 37. So 28, it's quite similar, so that's something you guys can think about. So what about 29 through 31? So write an equation for the nth term of the geometric sequence. Then find a sub 30th. Okay. So now let's put it right here. So write an equation for the nth term of the geometric sequence. So the way to do it, so we can always start it off with a sub n equals a sub 1 times common ratio to the power of n minus 1. This one is called the geometric sequence formula. So basically it tells you the shortcut, how to go from one term to the higher term. So a sub 1 according to the given series here, so that's 1. And then common ratio, in order to go from 1 to 4, we multiply everything by 4. So 4 to the power of n minus 1. A sub n, so that means it's going to be the number of the term. So if you try to evaluate it, or simplified it, so we just end up with the equation. So a sub n, so that equals 4 to the power of n minus 1. So write an equation, that's what we did, and then find out the n term of the geometric sequences. So the n term of the geometric sequences, that would be this one here. And then find a sub. Okay, let's see what that number is. Kind of blurry. So let's say that we want to find out a sub 9. If that's a sub 9, that means this one is just like a sub 9. So 4 to the power of 9 minus 1, so then that'd be 8. So 4 to the power of 8, so 16 times 16. So then that would be 4 fourths, and then 16 times 16 again. Okay, so this one, well, let's see, I think I did it wrong. So just 4. So you multiply 4 8 consecutive times. So 4 squared, that's 16 times 16 times 16 times 16. So it's going to be a big number. And then the next one is quite similar. So we want to find out that the also that one we want to find out a sub 9. So try to get a common difference first. So 5 times one number equals negative 10, multiplied by negative 2. Just like negative 2 times negative 2, negative 10 times negative 2, then that'll be 20. And from 20 to negative 40, so multiplied by negative 2. So what we found here, it's simply multiplied by negative 2. So try to get a geometric sequence formula. The common ratio, as you can see, that's a negative number. So it's a sub n equals a sub 1, so 5 times negative 2 quantity to the power of n minus 1. So 31, that's something you guys can think about it. And now let's go back to this page. So finding the common difference, recursive formula, we'll get to that for the next part of this. And write the first 6 term of the sequence, then sketch the graph of the sequence. So normally it's all about making the 6th term, okay? So you want to go from a sub 1 to a sub 6. Okay, so let's do one example like that. Okay, so now let's try this one. So write the first 6 terms of the sequence. Okay, again, we don't need to worry about the graph. So the first one is relatively easy. So what we found here, the first term is given already, which is 4. And then the second term, we plug in a number. So a sub n minus 1, that means the number we found from the previous term. So 4 plus 5, then that'll be 9. And then a sub 3, so using whatever that we had previously. And then you want to add 5. So for a sub 3, so this one will be a sub n minus 1 plus 5. So which is 9 plus 5. So it's going to be bigger. Okay, so making sure that the number you need to apply for this type of situation. Okay. And for a sub 3, I think I did something wrong. For a sub 3, instead of being 14, so this one is like a sub n minus 1. Okay, a sub n minus 1, that would be what, 9? And then 9 plus 5, yeah, it is, which is 14. So the question here is a little bit tricky because you need to apply the previous term before you evaluate the new expression. Okay, so now let's try another one. So a sub 1, that's negative 4. So a sub 2, which is negative 3 times a to the power of n minus 1. But we don't know what a sub n minus 1 is. So this one, nothing we can do about it. So we got a sub 1, we got a sub n, the formula. So we do know that n is 2. But nothing we can change with that a sub n minus 1. So this one, just leave it. Okay, so now let's see what else that we have for the rest of this. Write a recursive root for the sequence. So recursive root, that means it's just like a special pattern. You can come up with the number. So a sub 1, if the a sub 1 is 3, so what's a sub 2? 3 plus 5, right? So which is what? 3 plus... Okay, let's just start this one over. So a sub 1, we got 3 here. A sub 2, that's 8. And then a sub 3, which is 13. So to go from 3 to 8, we add 5. 8 to 13, we add 5. Okay, so this one to write the recursive formula. So then that'll be a sub n. So that equals a sub n minus 1. Okay, plus 3. But the next one here would be plus 5. Let's put it this way. So to go from 3 to 8, we need to add the odd number, add 5. From 8 to 13, we also need to add 5. 13 to, okay. So this one will be a sub n minus 1 plus 5. Okay, so for the next one, 3 plus 6 plus 12, 24, 48. So the pattern here, it's just multiply everything by 2. So 3 times 2, that's 6. 6 times 2, that's 12. 12 times 24, that's 12 times 2, that's 24. 24 times 2, 48. So for 36, the recursive formula would be written as a sub n. So that equals 2 times a sub n minus 1. So it depends on which one that the term you want to start at first. Okay, so now let's see what else that we have for the rest of the lecture video here. It's a long unit, it is. So it looks like we're kind of done right here. So writing the recursive formula. So 38 is quite similar. 37, it's also quite similar. So let's go back and do 37. So this one, it shows that it shows the 7, 6, 13, 19, 32. So 7 to 6. So it looks like subtract 1 and then 6 to 13. Then you increase the sequence, okay? So we do have 7, 6, 13, 19, and 32. So how do we rewrite the recursive formula for this kind of structure? So this one is one of the interesting one. From 7 to 6, and then 6 to 13, and then 13 to 19. As you can see that this part right here, it shows the pattern. From 6 to 13, we add 7. From 13 to 19, we add 6. And then 19 to 32. So that one, we basically add with 13. And 7 has nothing to do with the pattern here. So this one is one of the very good questions that you guys should think about, okay? So how do you write the recursive root for this kind of sequence? Alright. So pretty much we got everything that we have for this unit here. So you guys are more than welcome to rewatch the video. Fast forward, you have to, or go back to the part of the lesson that you still kind of struggle, or you want to have more explanation, or kind of missing certain kind of detail like what I explained it earlier. So always go back to it, check the work, the process, all that stuff. Okay, so one more time, let me go back, making sure that this one is the last section of this unit. It is. So thank you for watching the video that I have here today. So any questions I have, feel free to put into the YouTube channel comment bar, and I try to reply to you as soon as I can. So thank you for watching the video today. Once again, I'll see you next time. Take care.